In this episode of IdeaCity.
Most of the robots that you see today are fantastic. They're superhuman sometimes in their precision, superhuman in their speed, superhuman in their power, in their resilience, and their ability to work 24/7. But one of the areas where robots are really behind today is their ability to adapt.
IdeaCity, the smartest people, the biggest ideas.
Our next speaker, Hod Lipson, who's from Cornell, is trying to get machines to design machines, and then eventually machines to make machines. Hod, how are you?
So, most of the robots you've seen so far, and most of the ideas about robots that come to mind, usually for most people, barring the Hollywood fantasies, are kind of industrial robots that work in factories, that are very fast and very capable. Maybe surgical robots like the fantastic robot that's on display outside. Even entertainment robots that are carefully choreographed to produce music and things like that. And even house cleaning robots, such as this robot here. I have 3 of these at home. And I come back at the end of the day and they're all 3 of them huddled in the corner of the room and they didn't clean anything. So I don't know what, I don't know what they're doing. Maybe I should read the manual. So these are all fantastic feats of engineering, and these robots work relentlessly, and they've been laboriously designed by teams of engineers, and it's really a fantastic job. But the kind of robot that I want to talk about today are robots that are essentially were designed, manufactured, and programmed by themselves. So robots that can do that for themselves. And the main idea that I want to talk about is that if we really want robots to be smart and like humans and maybe even really do fantastic things, maybe we can't get there by programming and building them directly. Maybe we need to follow biology and let them learn, let them evolve, and let them do that by themselves. So that's the kind of things we look at Cornell. We look at robotics as a form of artificial life. And we try to see how we can push the boundary of what robots can learn and do by themselves. And we're interested in that to learn about life itself, to be able to have a fresh look at things like get a better feeling of what it means to be a human. How do we think? How do we act? How do we learn? So to give you an example, most of the robots that you see today are fantastic. They're superhuman sometimes in their precision, superhuman in their speed, superhuman in their power, in their resilience, and their ability to work 24/7. But one of the areas where robots are really behind today is their ability to adapt to new things. So adaptation is really one of the areas where biology is fantastic. So biology isn't very fast, isn't very accurate, but it's very good at adaptation. So one of the biggest frontiers and one of the biggest challenges today in robotics is making machines that can adapt to unstructured environments, to surprises, to changes, to things going wrong, and really figure out what to do. So these are the kind of things we'll look at. So I want to show you a couple of projects that we're working on. I'll go through a couple of them and try to look at different aspects of adaptation, of automatic design and manufacturing and so forth. So one of the fundamental questions is, can we have machines that will design themselves? And the idea is to use basically machine evolution to look at that. So this is a project we did a while ago where we said, you know what, instead of designing a robot from scratch, let's create a primordial soup of robot parts, bars, motors, joints, put them all in a big vat, and we'll do that in simulation, in a gaming simulator. and we'll let evolution do its thing. Evolution will combine these things in random ways, mutate them, take the better ones, and create offspring with small variations, and keep selecting them under Darwinian selection to make something that, let's say, can move or can crawl across the table. Indeed, after a while, a couple of days on a computer, and this is something that now will run on your cell phone, you can actually see interesting designs come out. And if you look at these are two robots that have been evolved to crawl across the table, their form and their controller. The one on the right almost looks like it was intelligently designed. It has this nice kind of arrow symmetric shape. It wiggles its tail. And these things work in reality. So here are two of these robots. They're evolved. Their shape, the control, the whole thing is a product of this simulated evolutionary process. So that's an example of how we can say, you know what, let's step away from designing these robots, trying to think, well, we can do everything, and let them take control of their own evolution and development. And of course, these are very, very simple robots, but the question is, how far can we push it, and how far can we go?
When we come back,
this machine was not programmed by a programmer. It was not modeled by an engineer. It created a self-model and used that to figure out how to walk.
get the latest Idealist news, presenter information, and watch streaming video at www.ideacityonline.com. IdeaCity, the smartest people, the biggest ideas.
Can we have a robot that can program itself automatically? And again, this is in contrast to most robotic systems active today who are programmed directly by humans, carefully choreographed to do whatever they need to do. And we know that, I think, will not scale if we really want to make machines that are adaptive, that can handle new situations that were not anticipated by their programmer. So this brings us this idea of self-reflection. Let me give you a little bit of an example of how that works exactly. So this robot here, this is a four-legged machine. It's actually outside. Later on you can see it. I think it's upstairs. This robot needs to learn how to walk. But the challenge is that it does not know what it looks like. When you look at this robot, you can see it's a four-legged machine. The robot itself does not know what it looks like. All it knows is that it has 8 motors somewhere, and it has 2 tilt sensors. So it has 2 motors on every leg, so 8 motors, and it has 2 tilt sensors. But it doesn't know what it looks like. It doesn't know if it's a snake, if it's a tree, if it's a spider. It has no clue what its shape is. And it needs to learn how to move forward. So imagine yourself sitting in a black box, okay, with 8 knobs. And you can turn the motors, and as you turn these knobs, the box tilts left and right, forward and backward. And you got to make this thing move. But there's no windows, there's nothing. How do you make something like that work? Maybe it's not unlike a brain in a newborn child, right? Needs to do all these things. So what this robot does, in the beginning, it moves its motors randomly. And it measures the tilt. And from this relationship of actuation and sensation, it gradually learns what it is. It gradually learns the shape that it has. And it takes it about a day to do that. It's a slow process. And in the beginning, it gets it wrong. You can see here it has no clue what it is. But gradually, as it experiments with itself, it begins to form a self-image. Okay, it begins to form something, some kind of self-perception, some idea of what it is. You see, it's beginning to realize that it has 4 legs, doesn't know quite how and where they're connected and so forth. But towards the end, it basically figured out that it's a 4-legged machine. It's not exactly connected the right way, not precise, but it's good enough so that we can ask it, okay, find a way to move your center of mass across the table, to learn how to walk. And we were hoping to get an evil spidery walk. But instead, we got this lame way of moving forward. But when you look at this machine, you have to remember this machine did not do trials of walking before. It was not programmed by a programmer. It was not modeled by an engineer. It created a self-model and used that to figure out how to walk. And so why are we interested in this kind of stuff? Well, first, from an engineering perspective, it would be great if robots can learn to program themselves. It saves us a lot of time. It saves us the laborious task of having to do everything explicitly. But more interestingly, if something changes about the robot, it can adapt. So this robot here lost a leg. And you can see fairly quickly it loses a leg internally. Its self-image also loses a leg. And it begins to limp. Now, it's not because we had a sensor there and we said, okay, if leg comes off, switch to plan B. No, it's not programmed in advance. All of this is spontaneous from the fact that it actually senses its dynamics change, its environment change, its self changed, and it figures out how to move without a leg. So that's an example of this adaptation process that comes from the ability to self-reflect and self-program. So where are we taking this? Right now we're looking at robots that don't just model themselves and self-reflect, but they also look at other robots. They try to model other robots to see what other robots can and can't do, what their intentions are, purely from observation. This is known in psychology as theory of mind, and it's an important factor, a critical factor in communication. Ability of people to talk to other people is the ability to understand what they are thinking and kind of reconstruct their mental processes purely from observations. And that's something that robots today are very bad at. And that's one of the reasons why it's not very easy to communicate with robots, because they're not able to do this kind of thing. So this is what we're trying to do now, is get robots to understand each other. And it's interesting to know that robots can actually model other things as well. So more recently, a couple of weeks ago, actually, we took the same idea and we said, okay, let's take a robot, it will look at something and try to understand what's going on. And we basically gave it a kind of, basically an apple falling from a tree, and it processed it for a day and came up with this relationship. This is what's going on, F equal ma. And was able to find out that energy is being conserved when the apple is falling. And so it's really exciting. We call this robotic scientist, basically the ability to look at phenomena, create models, understand automatically what's going behind them, what's driving. This actually was covered in the Seed magazine that we just received in our packages. And the New York Times had a headline, "Scientists have just found a way to replace themselves." So I think that's where we're heading. I think this idea that we can somehow program and design and manufacture machines that are as complex as we are is just not going to happen.
Great ideas are meant to be shared. Join the discussion on Facebook. IdeaCity, the smartest people, the biggest ideas.
Let's think about how we can have machines make themselves. How can robots build other robots and so forth? So, all these things are inspired from biology, because biology is really good at, biological machines kind of design themselves through evolution. They make themselves, they program. And we're really trying to understand all these issues, and how machines make machines, or how machines can self-assemble, is really a critical part of that. And give you an idea of where we're going with this, here are two building blocks for making robots. And the idea is that, again, when you look at most robots out there, they're monolithic. They are manufactured in a factory, they have one shape, they ship out, and that's it. They can't repair, they can't, it's just one physical structures. But imagine that we can make robots out of lots and lots of building blocks. For example, here are two building blocks. Each building block has 1 degree of freedom, so you can swivel, and we can attach these building blocks to each other, and we can make lots of different robots from the same building blocks. We can make an articulated arm one day, we can make a walking machine another day, all from the same small set of building blocks. And we can put them together in different ways. Maybe we have a gripper module and so forth. Now, this is interesting from a commercial point of view because it has an economy of scale, right? Because you're just making a small robot component from which you can make a large variety of machines. And in fact, there's a German company that actually took this module and is making this into a kind of modular robotic system. But the really interesting thing is that robots can make other robots out of these things. So you can have a robot that can take apart another robot and reconfigure it. Can come to a robot that's broken, replace one of the modules, and insert a replacement module so it can take care of itself. You can even have two robots gang up on one robot, take it apart, and use the parts for themselves, right? So you really have an ecology of machines that can actually take care of themselves. And this is from a proposal we sent to NASA with the idea that if you're sending robots to a remote planet, you don't want to send a monolithic robot that if it breaks, it's game over. You want to make robots that are made out of these components so that they can take care of themselves, they can adapt, they can self-repair, and so forth. But NASA didn't fund this. And so here's an example this is an earlier version of this robot. And this is a robot that has 4 modules. And the interesting thing is that if you feed it more modules, it can build a copy of itself. And that copy can then build another copy, and so forth. And so this is a very crude example of a self-replicating machine based on this idea of modular construction. So everything that self-replicates needs a supply of material and energy, and then it can make copies. So that's kind of where we're going with this aspect, and it's going to continue replicating and so forth. So, and we're trying to push this and to make these much more smaller modules. And here's another example. Let's say you have these modules that are made out of small things that can flip. And then it can attach to the neighbors and flip, just like this short animation showed. If we throw 1,000 of these modules into a big vat, again, of evolution, and we just watch what happens, if you look, so these things can flip around and connect and disconnect. Usually you get a primordial soup, nothing happens, these things connect. But once in a while, you get something very interesting. Okay, laser is not working. There. If you look in this area over here, you'll begin to see something really interesting. What's happening here is that in simulation, these robots here begin to self-replicate. Okay, they begin to move around, pick up other cubes, connect them, program them, release them, and these two things split into two, and these things gradually, these blue guys here begin to take over. And this is completely unprogrammed. So we're not rewarding, we're not programming them to self-replicate or anything like that. It just happens spontaneously because basically if there's no reward, self-replication, things that self-replicate just appear more and more compared to things that don't self-replicate. So self-replicate amplifies itself over time. It's kind of its own reward. And what we're doing now is trying to build these modular robotic systems instead of from these big crude modules. We're trying to make very, very small modules. These are about 0.5 millimeter on the side. We're trying to make robots that instead of being made out of 4 modules are made out of millions of very, very small modules so that they can really adapt. And so far we've been able to get these things to come together to form a piece made out of 10 cubes or 10 tiles. So there's still a long way to go before we can get to 1 million, but that's where we're heading. The other kind of thing that comes to mind, at least for me when I look at when I think about these projects, is that I think that as we move to more increasingly complex machines, there's no escape from handing off some of the programming, some of their development to the machines themselves. I think this idea that we can somehow program and design and manufacture machines that are as complex as we are is just not going to happen. We're going to have to hand off some of that and let biology, so to speak, do its thing. And so this idea that, for example, we can program 3 laws into every robot, that's not going to happen. It's really going to be much more of an evolutionary learning, and we'll have as much control over these robots as maybe a parent has over a teenager kid. Okay? You can implement, you can change your environments to some degree, you can influence them a little bit, but in the end, they learn what they learn, and you don't control what they learn and from who. And that's kind of the second point. And of course, all these issues come to, in the end, raise many interesting ethical questions, which is where are we going, and is this good? And you know, I used to kind of wave this off and say, you know, we just unplug it and we don't have to worry about it. But the truth is that this is really powerful technology, and scientists can't really anticipate and much less control where all of this is going. So I think this is why having this kind of conversation and dialogue is really important. Thank you.
Well done. That's fascinating. That's great.
You know, most of the robots you see is all programmed and choreographed, but this other big field of robots that is all about letting the robots do it themselves. So we are inspired to a large degree by science fiction movies. A lot of the students come to the lab are kind of sci-fi fans. You know, we see ideas, we see them, we read them in books, we watch them in movies, and we come and we try to make them happen in reality.